et bienvenue. Today we will be making some food. We do not know yet what it will be, but you follow us to the store and we will make the perfect meal.
Hello, my name is Tori and I'm your physics expert for this expedition. And I wanted to talk to you about a little bit about this car first. Although there's a lot of physics in cooking, we'll get to that later. I just wanted to point out that this is a huge car, so it's got a really high center of gravity. So we got to be careful when we're making those turns. But also, before we talk about center of gravity, I wanted to talk about the force that this car needs to be exerted on this car. Because of its huge mass, we have to apply a lot of force to get it to go. Much more force than if it was a smaller car. And also, I wanted to talk about the trip we're going to be making to the local Safeway. We are going to have a very large distance that we're going to go, but it's going to be a very small displacement. And if you join me in the car, we're going to see that. Let's go.
Okay, let's go.
Hello everyone, and thanks for joining me in the car. We're going to get started on our trip to Safeway right now, but first I wanted to tell you a little bit about the distance that we're going to be going. First we're going to go 0.9 miles at 0 degrees, and then we're going to go 0.6 miles at 270 degrees. This is going to give us a total distance of 1.5 miles. But it will give us a different displacement than that, and when we get back to the kitchen I'll show you what I mean. Let's go! Alexandra isn't a very good driver.
I have a question.
Yes, Katie.
How come when she makes the turn like that at a very high speed, I get pushed against the door?
That's because you have inertia. What happens is your body wants to keep going straight because your body has inertia, but the car turns and so your body moves into the door. That's another good reason we have these seatbelts on, because when Zan made that horrible stop, we would have kept going through the window if we didn't have our seatbelts on, but our seatbelts didn't have inertia.
Isn't that Newton's first law?
That is Newton's first law. Very good.
Whoa, an object in motion stays in motion.
Object in motion stays in linear motion. Very good, Katie.
Right.
And also, an object at rest will stay at rest.
Oh, right, of course.
Hello! We are here at the local supermarket. Is there any physics things about this you have to say, Tori?
Let's get something to bake. Look how much work I'm doing by pulling this off the shelf.
Actually, you aren't doing very much work because the motion that you're going is not in the direction you're going.
Not in the direction of the force you're applying. Very good, Katie.
Thank you, Tori.
But
I was
Katie,
a little confused.
why don't you guys put the boxes on the ground?
Oh, this is so difficult.
Now you're doing work. Let's see who has the most power. Both of you put your boxes on the ground. Now let's see who can pick it up the fastest. Zan is the most powerful. Katie is the most bitter. Not bittersweet.
Well, class, it looks like it matters more what we like and not what you like. So we're making cupcakes. Deal with it.
Hello everybody, and thanks for joining me in the kitchen today. Now before we get started with cooking,
Hello.
I want to talk to you a little about the physics that we observed when we were in the car. So before we went, we talked about the total distance we traveled. First, we went 0.9 miles at 0 degrees, and then we went 0.6 miles at 270 degrees. And 0.9 plus 0.6 gives us a total distance of 1.5. But there is a difference between total distance and total displacement. Do either of you know what that is?
I do. Well, actually, displacement is how far away you are from your starting point, and distance is how far you've traveled.
Very good, Zan. Now let's find our total displacement. And we can find that using vectors. So let's find our vector. So first, to find our vector, we can use the Pythagorean theorem. The what?
Pythagorean theorem.
The what?
Pythagorean theorem.
Very good. So first we add 0.9 plus 0.6, 0.9 squared plus 0.6 squared, which equals our vector squared. So if we take the square root of 0.9 squared plus 0.6 squared, we get our total displacement, which ends up being 1.08 miles. Now let's find the angle from
the kitchen where we started to the Safeway we went to. And to do that, we take the tan of theta, which is seen right here, of the opposite, which is 0.6, over the adjacent, which is 0.9. And you can see that work right there. Tan of theta is equal to 0.6 over 0.9. And when we do that, we get an angle of 33.69 degrees. Now let's go to cooking and see how physics is used in cooking.
Salut! Thank you for coming back to the kitchen with me. Before we start mixing the ingredients together, we need to make sure that we measure them out very accurately. Accurately is different than precision. Accurately means close to the accepted value. Like this. This is very accurate to 1 tablespoon. Now just 3 more. 1, 2, 3. Hip, hip, hooray. Fini.
Kitty, mon ami, your eyes, they are like the stormy nights, stormy skies of the black abyss of my hometown.
You're on.
Oh, hello. Salut. Now we must crack the eggs. In order to do this, we must exert a force over a period of time. What's that mean, Sam?
We are going to gather some momentum
And use impulse. Ready?
to stop the egg and crack it.
Go! Yes! That is beautiful. 2 wonderful eggs right in our bucket.
So can you explain what you did? As you took the egg and pushed it down, it gained momentum, and as it hit the bowl applied a force over a period of time or an impulse which cracked the egg.
Yes, exactement.
My arm gained lots of momentum.
So now we have all our ingredients ready to be mixed. So what we are going to do is apply torque, which is a start or stop of motion.
Well, actually, Katie, it is a force needed to start, stop, or change the direction of a rotation. So you can rotate your whisk like so, and it will apply a force.
Exactly.
Also, if we used an electric mixer, like I said, the electric mixer would have torque.
But this also has torque.
Yes, it does. It also has torque because it has the force needed to start a rotation.
Technology is getting too widespread.
Thank you for joining us tonight. It was a bonne nuit.
It was a bonne nuit.
Oh, yes.
Au revoir. Now, it's important to note that we are making sugar-filled cupcakes. Before you eat one of these, you should have a balanced meal, like this soup right here.